You have to be able to explain how arithmetic shifts work, demonstrate that in an exam, and explain that arithmetic shifts are suited to division and multiplication of negative numbers. So let's just practice so we can understand how to perform the arithmetic shift to the right. So remember, shifting to the right is going to carry out division by 2 for us, and because they are mostly negative numbers that this is aimed towards, we'll just practice it with 2's complement negative numbers. So if we use this as an example, and we have to first work out what that value is as a negative. So that value here is -8. Now hopefully you can work out that the result should be -4. So what we'll do, so we can check a result, is we will write down what -4 should be, assuming 2's complement notation. Now -4 in 2's complement notation is 1, 1, 1, 1, 1, 1, 0, 0. Now hopefully you understand how to do that because you've completed the 2's complement section. So performing an arithmetic shift right, the first thing that we want to do is preserve the most significant bit so that the sign of our number is not changed. And then we do the same process really as we did with the logical shifts. We move every bit one position to the right, doing it slowly so that we don't make any errors. And then with the least significant bit here, we can just forget it. It's also moved along, but it's just trashed because we only have 8 bits. And hopefully if we look and compare our two numbers, we have achieved the same result. So we've shown that the arithmetic shift right, when we preserve the most significant bit, works. Let's try an arithmetic shift right this time. And we will start with the binary number 1, 1, 0, 0, 1, 1, 1, 1, which should be -49, assuming 2's complement. And what we want to do by shifting to the left is carry out a multiplication by 2, which should give us the result -98. Now -98 in 2's complement is 1, 0, 0, 1, 1, 1, 1, 0. So if we perform the same steps as last time, I like to always just write down the most significant bit again, just like in sign bit, just remembering that it's negative. But this time, because we're doing a logical shift left, the new number, the 0, is shifted in at the right hand side. So we shift in a 0 and then move the rest of the bits one place along till we get to this last piece here. Now in this instance it doesn't change anything, but if it was a 0 it would completely ruin our number that we've got represented, so we can just disregard this last one because the most significant bit's already set. Now if we compare the two numbers, then we'll see that they are an exact match and that the arithmetic shift left technique also works. Now these are quite difficult. I suggest that you really practice them until you understand it and can explain how to do them.